All right, welcome back everyone. In a previous video, I promised you that I would work out example 3 and example 4 from this section, chapter 2, section 2 note sheet. So real quickly, what I'm going to do is I'm going to work through these two proofs, showing you how I complete these. We would have done these in class, but if for some reason you missed it, or you just want to kind of walk through it again, that's what this video should help you with. So in example 3, we have this diagram here with a bunch of angles happening. We have a larger angle ABC that's been broken into angles 1 and 2. We have another larger angle DEF that's been broken into angles 3 and 4. So you got ray BG breaking angle ABC into two smaller angles, and segment EH breaking angle DEF into two smaller angles. And in the given information, it says that angle 1's measure is equal to angle 3's measure, which we know means that they're congruent, so we've marked them congruent. And the same thing about angle 2 and angle 4. Their measures are equal, so we know that means that they're congruent. So this is what we know. And our job is to prove that the measure of angle ABC, right here, is equal to the measure of angle DEF, right there. Right? So how does this information prove that that's true? This is actually going to look very similar to example 2 that we did. In example 2, we were talking about segments, and the fact that if they were broken into two congruent parts, that the segments themselves actually ended up being congruent. Now we're just going to be looking at angles. So the statement number 1 just says that measure of angle 1 equals measure of angle 3, and measure of angle 2 equals measure of angle 4. That is our given information. In statement 2, we said that if we add 1 and 2 together, it's the same as adding 3 and 4 together. Well, why is that true? Well, I know that 1 and 3 are equal, and that 2 and 4 are equal. So this is back to that idea of if A equals B and C equals D, then A plus C equals B plus D, right? We talked about that back on the part of the notes when we were going over the different properties from algebra. And this is the addition property. 1 is equal to 3 and 2 is equal to 4. So if I add these two together, it's the same as when I add these two together. So this is the addition property. Technically, it's the addition property of equality. In statement 3, we said that if we add 1 and 2 together, we get ABC. Well, let's look at where that shows up. How does that show up in our diagram? Here's 1, here's 2. If I add those together, I get ABC. Well, yeah, I know that because of the angle addition postulate. And the same idea with this other angle. If I add 3 to 4, I get DEF. So this is the angle addition postulate. That's what tells me that this pair of statements has to be true, the angle addition postulate. Lastly, it turns into that the measure of angle 3 equals the measure of angle DEF. Well, here's angle ABC. I think I said measure of angle 3. I meant measure of angle ABC equals measure of angle DEF. Here's angle ABC. Here's angle DEF. Now, those are angle ABC is equal to 1 plus 2. Angle DEF is equal to 3 plus 4. But up in statement 2, we said that 1 plus 2 equals 3 plus 4. So if I turn this 1 plus 2 into an ABC, I have this. If I turn this 3 plus 4 into DEF, because of what it says in statement 3, I can do that. I have that. So that is the substitution property. Because all I did is I took the 1 plus 2 in statement 2, and I substituted ABC for it. I took the 3 plus 4 in statement 2, and I substituted DEF for it, because it says in statement 3 that ABC equals 1 plus 2 and DEF equals 3 plus 4. So there's my proof for that one. Again, like I said, it should look pretty familiar. It should look pretty similar to example 2. Now in example 3, we're going to have something a little bit different. Given that segment ST would be congruent to segment RN, or that the distance from S to T is the same as the distance from R to N, and that IT equals RU, prove that SI must equal UN. Now it kind of makes sense that this would be true, right? If this longer segment is congruent to this longer segment, and I take out the same amount from each segment, it would seem to make sense that this would end up being the same as this. You know, what's left over after I take out IT would be the same distance, the same length as what I have left over when I take out RU. But we can actually prove that it has to be true. So let's look at that. In statement 1, we just say that ST equals RN. Now I know that that's true because it is given to me. It's right there. Then I have blank equals SI plus IT. Well, what would SI plus IT combine to give me? They combine to give me ST. And how about RU plus UN? They combine to give me RN. What's the reason? How do I know that ST is equal to SI plus IT and that RN is equal to RU plus UN? That is the segment addition postulate. The segment addition postulate. Now in step 3, I've said that SI plus IT equals RU plus UN. How do I know that's true? Well, let's look at where these this phrase comes up in from statement 2 and statement 1. SI plus IT is right here, saying that it's equal to ST. RU plus UN, so I like to color code things, so let me put the same color box around those two things. And then RU plus UN shows up right here. So now if I color code RN with this RN plus UN and ST with this SI plus IT, where else do I see ST and RN? In statement 1, where it says that they are equal. All right? So what's happened here is I took statement 1 and I turned the ST into SI plus IT because those two things are equal. I took the RN and I turned it into RU plus UN because those two things are equal. So this is an example of the substitution property in action. The substitution property. Now I said before that we abbreviate a lot. Don't abbreviate substitution as SUB because then you might think it's subtraction instead of substitution. So you probably want to spell out all of substitution. In number 4, statement 4, we have IT equals RU. How do I know that IT is equal to R? Oh, that was given, right? So that's easy. I can just put given there. Now, lastly, we have our last statement, which is blank. Well, we know that the last statement of any proof is always going to be the thing that we're trying to prove, right? That's when we stop, when we've stated the thing that we're trying to prove. So I know this last statement will be SI equals UN. But how do I know it's true? Well, where does SI show up? It shows up on the left side of statement 3. Where does UN show up? It shows up on the right side of statement 3. So how does IT and RU go away? Well, in statement 4 we said that those are equivalent. So if I take off the IT here, and if I take off the RU here, that move is allowable because I am essentially subtracting the same thing from both sides of an equation. So what does that call? What allows me to subtract the same thing from both sides? It is the subtraction property of equality. And again, like I said with substitution, spell out subtraction. Don't just put SUB. Subtraction property of equality. And so there I have it. Now that's how I know, even though common sense told me that yes, SI should be the same as UN if all this other information is true. Now I've proved it. Now I've proved that it has to be true. All right, folks, that's it for this video, and I will see you next time.